Come down to the water with me. The dawn mist is clearing, and a young blue heron named Wren is standing near the reeds, trying to find her missing sister. The problem is, she only knows her sister is somewhere in the reeds. In a wetland this vast, a description that vague gives her almost nothing to go on. Without a shared, standardized way to measure space, trying to communicate an exact location relies entirely on guesswork. This overhead map reveals a natural solution. The pond where these rivers meet is our origin. The East River creates the horizontal axis, measuring across. The North River forms the vertical axis, measuring up. Reliable navigation demands a sequence: across first, then up. By combining one fixed origin point with two perpendicular axes, we take an infinite, unmapped space and turn it into a mathematically precise grid. Let's see how this works in practice by checking on three friends resting on the grid: a heron, a frog, and a fox. This coordinate plane shows their exact positions. The heron sits at the coordinates 2, 4. The frog is far to the east at 5, 1, and the fox is mid-meadow at 4, 3. Looking at these numbers, we can solve a specific analytical problem. Which of these three animals is resting furthest north? We can find out by completely ignoring the horizontal distance across and isolating only the second number, giving us the vertical measurement. Comparing those vertical measurements alone, we see the heron's value of 4 is the largest. That proves the heron is furthest north. The coordinate system lets us isolate, measure, and compare one physical dimension entirely independently from the rest of the variables. Now, let's bring our focus back to Wren's immediate goal: defining the exact location of the lily pad where her sister is waiting. We have the raw distance measurements to her target. The lily pad is exactly 6 meters across to the east and 2 meters up to the north. This diagram plots that path by formatting those raw measurements into an ordered pair. By placing the horizontal value first and the vertical value second, we create the formal address, 6, 2. Locking these orthogonal measurements into a specific sequence like this guarantees a single, unarguable location that anyone can find. Curious, but what happens if someone assumes the order of those numbers doesn't actually matter? Take Tella the painted turtle, who thinks the coordinates 1, 4 and 4, 1 are essentially the same place. This plotted graph shows the outcome of her first coordinate. Measuring 1 unit across and 4 units up places her near the reeds. Reversing the sequence changes the destination entirely. 4 units across and 1 unit up lands her out by the far bank. There's another way the system can break down. Imagine Pip the fox scratching a map in the mud with points dotted everywhere, but no labels, units, or directional markers. Numerical coordinates mean nothing if the reader doesn't know what measurement scale the axes represent. A mathematical framework only works when the sequence of the numbers and the definitions of the units are universally applied. Pinpointing a specific location comes down to the integration of these tools: the starting angle of the origin, the perpendicular axes that define the scale, and the consistent sequence of moving across before moving up. Following those coordinates, Wren takes flight. She travels across the horizontal axes, then turns up the vertical axes, arriving safely at exactly 6, 2. The coordinate plane takes the unpredictable physical world and translates it into navigable order.